Welcome back. We are talking about wastewater treatment. In this video, we'll be discussing about the primary treatment of wastewater. And primary treatment, we are mainly taking the treatment through a primary clarifier or primary sedimentation tank. This is only by simple gravity. And what are the particles which settle down to the bottom? They are called as sludge because they're coming through primary sedimentation tank. They are called as primary sludge. So we'll talk about the design parameters of the primary clarifier and a simple calculations. There are two shapes of primary clarifier, circular and rectangle. In general, circular clarifiers that are more preferred in wastewater treatment plants. Now this is the sedimentation tank, primary sedimentation tank, circular in shape. The water will be entering from the bottom and then enters here. Then there will be a distribution channel here around 1 to 2 meters, around 1 meter below the water level. And then water slowly enters into the tank radially in both the directions. And after the treatment is completed, this wastewater will be going through a outlet channel here. This is the outlet channel, and this is along the circumference of the entire sedimentation tank. So now you can see here, this is the shape of the tank. So this is the entire sedimentation tank. And now what you are seeing is that this is circumference. Outside the circumference, we are having outlet here. And this is what we are going to talk about in this. And the purpose of the primary sedimentation tank is to remove particles greater than less than 0.2 mm in size. And it can be rectangular or circular. Sedimentation by gravity is the principle. Design should be made for average flows and checked for peak flows. The ratio of peak flow to average flow is around 2.5 to 3. Detention periods are 2 to 2.5 hours. The wear loading for average flow generally should not be greater than 100 meter cube per day per meter. That means per 1 meter run of circumference, it should not be discharge should not be greater than 100 meter cube per day. In circular tanks, the diameter should be less than 30 meters. So this will enable the working of scrapers which are provided at the bottom. So that larger diameter will be making difficult for the scrapers to move around and collect the sludge. And the sludge collected at the bottom through the scraper is now collected out from the bottom through an outlet pipe. The bottom slopes here, this is the bottom slope, around 8 to 10%. Similarly, we are also having rectangular tanks, and they will be 1.5 to 7.5 L by B ratio, and L by H ratio is around 5 to 25. And longitudinal slopes are around 1%. Maximum values of length is 90 meters, and width should be 30 meters. They are not regularly used in the wastewater treatment, but exceptionally they are used for specific purposes. There are some design values here. Then the primary sedimentation should be followed by secondary treatment. And there are different options. Based on the options, the surface overflow rate is fixed here. Average flow and peak flow, the two are separately considered. When you're talking about only primary settling, the average flow should be around 25 to 30. But usually, when the accurate sludge process is followed after primary settling, 25 to 35 meters per day. And some other treatment, secondary treatment is followed after primary, it is around 35 to 50. And peak flows are usually, you can see here, 2 to 3 is the range. and depth of the tank is around 3 to 3.5, and activated sludge it is around 3.5 to 4 meters. The suspended solids shall be removed in the sedimentation tank, which is around 45 to 60%. Because the settling, some inorganic solids also will be settling down. Along with that, some BOD is also removed. So 25 to 40% of BOD is removed in the primary sedimentation tank. The rectangular tanks, minimum depth for primary sedimentation tank should be around 2 meters, 2.5 meters for secondary sedimentation tanks. And the circular tank inlet baffle. So this is the inlet baffle. This is 10 to 20% of diameter, extending 1 to 2 meters below the water surface. V notches we normally provide here. V notches are provided to find out the amount of water coming out through the sedimentation tanks. And they should be having a maximum 50-meter depth with 0.2 to 0.3 spacing all around the circumference. Here, one more thing we should notice, what are the scum, the oil particles which are collected at the surface, they can be collected through a scum removal system. So here, the scum will be scrapped from the top scraper. This is scraper here. So now this is when you're moving it through, then automatically these oil particles are scrapped out into a separated trough collected at this top surface. Now let us look at a small problem. Design a circular sedimentation tank, primary sedimentation tank, to handle an average sewage flow of 5 mld. Assume suitable data. Suppose I'm assuming 2.5, 2 to 3 is usual values. So 2.5 is the peak factor I'm assuming here. So peak flow will be around 2.5 to 5, around 12.5 mld. So it's equal to 12,500 meter cube per day. And 5 mld is the average flow, which is equal to 5,000 meter cube per day. Surface overflow rate, if it is only for primary sedimentation tank, it should be around 25 to 30 meters per day. So area required will be equal to discharge divided by surface overflow rate, 5,000 divided by 25, which is equals to 200 square meters. So using this area, we calculate the diameter of the circular tank, comes out to be 16 meters, which is less than the 30 meters, which is normally adopted. And within the range of 2 to 2.5 hours of detention time, if we assume 2 hours of detention time, volume of the water in the tank will be equal to area multiplied by depth, or volume is equal to discharge multiplied by time. So discharge is equal to 5,000 meter cube per day. So it should be converted into hours by dividing with 24 and multiplying with 2 hours. We are going to get 417 meter cube. So area we know, volume we know, and hence liquid depth we can calculate H is equal to V by A, which is equal to 417 by 200, which is equal to 2.08 or 2.1 meters, which is less than the maximum value of 3.5 meters. Weir loading, this is total wastewater flowing along the circumference, that is pi d. So discharge per circumference, 5,000 divided by pi into d, which is around 100 meter cube per meter per day. For average flows, it should not exceed 100 meter cube per meter per day. So it is also satisfied. For peak loading, if you look at the surface area provided is 200 meter square, and peak discharge around 12,500. So which is close to the higher value of 60 meter per day of surface overflow rate. So then weir loading at peak flow rate is again discharged by pi d, which is around 250 meters cube per day. And we have the bottom slope, if you assume, which is equal to 10%. And what you're having is this is the bottom slope. In this particular problem, this is the bottom slope. This is the bottom slope. So that means this value is nothing but this is the bottom slope we are talking. So I'm taking one particular portion here. So this is my d by 2. And if I take this vertical depth as y, that is what I have to calculate. So y by d by 2, vertical to horizontal, is equal to 10%. It is nothing but 10 by 100. So total diameter is equal to 16 meters. D by 2 is equal to 8 meters. So y by 8 is equal to 10 by 100. So y is equal to 0.8 meters. And hence the total depth will be equal to the freeboard plus water depth plus bottom slope. Uh, and if you're assuming a freeboard of 0.5, total depth will be equal to 3.4 meters. So this is the total depth of the tank. Now we'll see another rectangular primary sedimentation tank for the same data. So 2.5, we are assuming peak flow to average flow. So the 12,500 will be the peak flow, 2.5 multiplied by 5 mld. And average flow is equal to 5 mld, which is equal to 5,000 metric cube per day. And as in the previous case, we are having 25 meters per day and average flow SOR. So that the surface area required is 200 meters square. So now as per the guidelines, we can have L by B ratio up to 2, around 2 I'm taking L by B ratio. We are having some numbers 1.5 to 7.5. I'm taking 2 here. So L A is equal to L into B, that is equal to 2B square is equal to 200 meters square. So B is equal to 10 meters and L is equal to 20 meters. And the time is equal to 2 hours if we assume volume is equal to 417 meter cube and the liquid depth is equal to volume by area, which is around 2.1 meters. When peak loading, we have to check what the peak loading divided by area, whatever we have provided. If you look at that, that is again close to the higher value of 60 meters per day, as in the previous case. Longitudinal slope, you are taking 1%. Again, if you look at this diagram, this is the rectangular sedimentation tank. Here, what we are observing is this wastewater is entering, this wastewater is entering through inflate channel and enters into this particular tank. This particular portion is the nothing but the rectangular portion of the tank. And the particles will be flowing across a baffle into this tank. Baffle is only to direct the water into this rectangular portion or settling zone. All the particles will be settled down under the bottom of this rectangular portion. And what we are doing is we are making a sloping surface here, usually around 1%. Is what we are calling as longitudinal slope. And all the particles which are settled down, they will be pushed down to a sludge hopper by using a belt conveyor system. So this the belt will push all the particles into this sludge hopper, and the entire sludge collected here, they will be pushed out from the hopper using a sludge withdrawal mechanism. This belt will be run through a driver here, and all the treated water after settling will come out again through overflow weir. This is a weir here. This will enter into the outlet channel. From there it goes out. And here we are providing a number of weirs along the length width of the tank so that the water flowing across the outflow weir can be adjusted. So what I'm talking is the length is 20 meters. So this is the length of 20 meters. And this is the water depth is 2.1 meters. And the width will be perpendicular to the direction of the screen. And this is the longitudinal portion. So 1 by 100 is equal to, say, y by 20. So it is equal to 2.2 meters. If I assume a freeboard 0.3 to 0.5 normally provided, suppose if I assume to 0.3 meters, total depth will be equal to freeboard plus water depth plus this sloping surface, which is equal to 2.6 meters.